left 290 degrees 8 knots.
This is the Airbus A380, also known as the Super Jumbo Jet. I'm setting out on a journey to uncover the A380's hidden links to brilliant ideas from across the world and throughout history. I'm about to reveal the engineering connections behind the biggest airliner the world has ever seen. You can't help but just be stunned by the sheer size of the thing. It is the only aircraft where the passenger seats run the full length of the fuselage from front to back on both the lower and upper decks. The cabins are 6.5 meters wide. It's the width of it. And 50 meters long. It is huge. The A380 can carry up to 853 passengers, 35% more than its nearest competitor. It's big. It's very big. The wings are immense. 70 family cars could park on each one. But if the wings are too long, it can cause problems. It stands to reason that the world's biggest airliner is going to need the world's biggest wings. And they are absolutely huge. The total wingspan is almost the length of a football pitch. They have to provide enough lift to get 560 tons of people and machinery off the ground. But believe it or not, if these wings were built to a conventional design, they'd need to be even longer, and the A380 wouldn't fit into most of the world's airports. There's no good being able to fly if you've got nowhere to fly to. There are international restrictions on the maximum size of aircraft to avoid collisions as they taxi around airports. The absolute limit on wingspan is 80 meters. The A380's wings must be short enough to fit regulations, yet they must still create enough lift to get the world's biggest airliner into the air. The Airbus designers found a brilliant solution by drawing inspiration from the animal kingdom. But how did they do it? I'm about to take the first steps in my investigation. Aerospace engineer Dr. Peter Barrington thinks I should get a feel for how a conventional wing creates lift. And the best place to do that is in his wind tunnel at the University of Kingston in London. Peter's given me a handheld smoke generator so I can make the airflow visible. So, Peter, how does it work and how can this help explain it?
Okay, well, basically the key thing to a wing is the cross-sectional shape. And that bends the air around the wing. The wing is able to make the flow go a lot faster on the top than it goes on the bottom.
The shape of the wing is designed so that air moves faster above than below. As a result, the air above the wing is at lower pressure than normal. So the higher pressure underneath the wing pushes upwards, creating lift for the whole aircraft. You do get the sense that lift, flight, is just a function of that shape of the wing. That's all it can do. The same smooth flow of air creates lift all the way along the wing. Or almost all the way. Peter's about to show me that conventional wings have a serious downside.
If you move a bit this way, see what happens as you come a bit closer to the end. A bit closer.
Out to the tip of the wing.
Exactly, yeah.
There it goes. The airflow at the wing tip looks completely different. Instead of a clean, steady flow, there's a spiraling whirlpool of air. It's called a wingtip vortex. High-pressure air from underneath the wing is leaking around the wing tip and pushing down on the top surface.
That last 5% of the wing isn't really doing anything for you. It's not generating much lift.
The vortex means the wingtip doesn't provide any lift. So the wing is longer than is really necessary. And for the Super Jumbo Jet, that's a supersized problem. This A380 prototype was launched through a curtain of illuminated smoke. The test showed that the world's biggest wings would suffer from huge vortices at the wingtips. To compensate for the loss of lift, the A380's wings would have to be made even longer. Too long to fit in with airport size regulations. The Airbus designers had to find a way to clip their wings down to size. And it's a story that reveals the secret of soaring like a bird. For the next stage of my investigation, I'm meeting another leading aerodynamics expert. But I hear he can be a bit difficult. His name is Cossack. And he's a steppe eagle, a species named after the wide-open plains of the Central Asian steppe. I'll be honest, he's a big, impressive-looking thing. Cossack is a scavenger by nature, and his lifestyle gives him a very similar problem to the A380. He's gone. To soar high above the plane in search of food, he needs a thermal, a rising column of warm air around 20 meters wide. But like the A380, his wings can't be too long, otherwise his turning circle will take him outside the thermal. So his wings are perfectly adapted for maximum lift with minimum length. And today, he's agreed to take part in an unusual experiment. Oxford University zoologist Graham Taylor is going to show me exactly how Cossack deals with wingtip vortices by filming his wings in flight.
So these are little wireless video cameras.
So you can fit cameras to him?
Right, this is the tricky bit.
What do you do with that?
And I try and put this in his face.
Cossack's handlers help him into the Eagle Cam harness. And now he's ready for his close-up.
Okay.
Wow. With a bit of luck, what we're hoping for is that these cameras are pointing along the wings, aren't they?
That's right.
So we might actually see how they work and what they do. It's fantastic. Right.
It's blowing in the right direction for good flight.
Yes, yes, yes. There you go, there you go. Yes, yeah, there's a beauty. Cossack heads for the wide blue yonder, this time broadcasting on Eagle Cam. There, you can see it. That was right along the wing. Is that what we're looking for?
That's what we're looking for.
Cossack can manipulate the feathers at the tips of his wings. To get maximum lift, he curls them upwards until they're almost vertical. This is the key to getting rid of wingtip vortices for highly efficient flight.
When it's actually soaring around in thermals, what you'll see then is that the wings are taking a heavy load the whole time. And as it does that, those wingtip feathers are curled up the whole way through that it's turning around.
It's disrupting this vortex that rolls around the end of the wing.
That's right.
Cossack's using his tip feathers to create what's called a winglet. This natural adaptation acts as a barrier against the vortex, blocking the path of air as it tries to flow around from underneath his wing. So he doesn't need long wings. His shorter, more efficient wings do the job. The question is, can engineers apply the same trick to these wings? And this 560-ton bird, the Airbus A380.